Welcome to all. I forgot to write the class number. You can see in the title there. I think class number 54, I think most probably. Part 2. Maybe lecture number, I think 13 or 14. See there. Now, right now we are in Lami's theorem. One class is pending for Lami's theorem. I told you. Suppose some object is hanging and you support it by two ropes or cables. How to find tension? That is a very important question for Lami's theorem. But I told you how to find tension, something which never came so far in our class. And first of all, you should remember one thing now. See, today's title, how to decide and mark or show, how to decide if a sketch is already existing, if someone is showing the force, how to decide, or if you want to show it, mark it, how to mark compression and tension. I will limit my explanation right now to engineering mechanics. First remember, in engineering mechanics problems, so many times you consider some cable or wire supporting something. Then it will be in tension. Sometimes a member may be placed in between, subjected to a force like this. Okay. Then it will be in compression. You should correctly know how to mark tension compression or compression or tension. Now, before you go further, go through this class completely. Before you discuss that one important aspect. This tension or compression, that is called axial force. Brief I will tell now. Don't worry now. It is called axial force. When you go to strength of materials, axial force will come. Usually symbol is P. Symbol is P. Little later in strength of materials, another term will come called shear force. Symbol is V. Then you will get one more term called bending moment. Symbol will be M. Last term will be torsional moment or twisting moment. Symbol is T. These are backbone or the complete what you can tell. It's a backbone or this is required for design purpose. When you design a structural member, you design for resisting axial force, shear force, bending moment and twisting moment. These are called section forces. Section forces. Why? Because they are resisted by cross section. They are not transferable. If you apply a load on a member, see, the load is transferred to support. But the cross section of member is subjected to section forces. Axial force means compression or tension, shearing force, bending moment or twisting moment. They cannot be transferred. They should be resisted. So these all we will discuss in strength of materials, not now. Engineering mechanics, we require how to decide or how to mark. But one thing, concept is concept. So more details of this will come in strength of materials. But at that time, see, when you go to pin jointed frame, you have to mark tension compression. Then I will tell on that day. I will briefly tell on that day, but I will tell then. Do one thing, go to engineering mechanics class uploaded, maybe class number so and so, part so and lecture number so and so. Refer, study today and come back. So this I will remove. This is not right now required for us. Right now, don't worry about these things. And there is one more wrong concept used throughout the world. Not only in my country. So many places, even I have seen established structural engineering institutes or structural engineering places. People tell axial force, that is compression or tension, or shear force or bending moment or twisting moment, torsional moment, they are internal. 100% wrong. They are completely out of track. They are not internal, they are external. I will prove it, not right now. A separate class I am uploading for that one. The wrong concept of telling these four, axial force, shear force, bending moment and torsion as internal, I will tell them, open your eyes, at least now learn. It is not internal, it is external. Reason I will tell, after going to that class, maybe it will take around 1.5 or 2 hours. So many examples I will give. Then the person who up to that stage was telling it is internal, suddenly he will tell, oh, I was wrong all these days. It is external. I will prove it. Internal is resistance. So many examples I can give, but right now, I will see that people will change their attitude of telling it internal, it is external. But right now, don't bother. A fitting reply will be given for those who tell wrong concept. Purpose is not to insult, at least to make them awake or let them learn. Don't make the mistake in future. That is my purpose. Right now, I won't tell about it. Now see. Class, something I tell, this only class. Tension, compression are very, very powerful terms. It is tension, compression, together it is called, any one of them, axial force. Next one is shear force. Next will be, see, bending moment. Last will be twisting moment. These are all classes. And what I want to tell, it will be very, very systematically discussed in strength of materials. But from engineering mechanics point of view, I am continuing now in the class. So, but learn everything. Okay, start now. Consider a member subjected to axial force P externally as shown. See here. You take a member. You apply axial force P this way and same force P this way. Member should be in equilibrium. You should write it. P as shown and you should write here. Member in equilibrium. Member in equilibrium. Equilibrium. See now, how? See here. P, inward acting. I will tell in the class, when you tell compression and tension or bending moment later, do not use direction like right side, left side. When you define a force, you tell right side, left side, positive, etc. Correct. But when you want to talk about compression or tension, do not use what? Direction. Use nature. And one more thing I will tell in the class. When you want to explain external forces or equilibrium, see, right side, left side, upward, downward, clockwise, anti-clockwise, direction based. You can see I am using only one hand. But when you want to show somebody section forces, you should tell, see, both hands are required. No left, right. See, compression, tension. See, two hands required. Shear force. One hand you can't bend. See, bending moment, twisting moment. See, one hand, can you twist it? It will rotate. Suppose this cloth, I will dip in water. I want to remove the water. Can I do this way? I cannot do this way. See, I have to twist this way. That is twisting moment. This all I will explain in strength of materials class. So, both are equal forces P. See, two cases are there. Case 1, case 2. Case 1, I am applying the force both inward, see, this way. Second case, I will apply outward, this way. Now, consider one, class. Class means I am telling something, you write. Same thing I will tell here also, class. I'm discussing what? I'm discussing case 1 now. See here, this case. This member is in compression. And compressive force equal to P. Don't tell P minus P like that. One more thing is there. When you decide section forces, wherever you want, you have to consider only one side. See, if I look this side, compression P. If I look this side, compression P. See, later, if I look this side, tension P. If I look this side, tension P. You should look only one side. That all comes in strength of materials. Considering only one side, all reasons will be there. So, member in compression force equal to P. Later, I will come to consider case 2. I will tell now only. Class. This member is subjected to force like this. Member will be in tension. Tensile force equal to P. Now, class once again. See. If you apply force, my hand is paining now because I hit very hard. If we apply compression force P, member has to resist it. Otherwise, it will keep on deforming. See here, if I take a cloth and apply compression, see here, it will keep on deforming. Yes, but if I take a solid member, see, if I apply compression, you can see member slight deformation is there. See now, it is in equilibrium. So if you apply this way, you see what the member will do to your hand. You take this way and press it. If you press this way from outside compression, you can feel the member pressing you back. See, it will actually press you back here, press you back here. Or simple example, I have to slightly up to here I can see, I think most probably. Okay, see now. Suppose I am an internal part, a member. I use my both hands this way. This way. Somebody from outside is pressing me here, I do not want to move. My hand I want there only. So if he pushes this way, what I will do? I will push him back. See? I will push him back. See here? This is internal resisting force for resisting externally applied compressive force. Same way here. See, if I put this way, suppose someone will tie a rope here. Suppose they pull you outwards. Then what you will do? If you do not want your hand to move, if they pull you outwards, you will pull back inwards. See, inwards. This is internal resisting force for resisting externally applied tension force. See, so many people who tell section forces are internal, they will use some places. Consider a member subjected to axial compression. I will tell them. You told just now, consider a member subjected to axial compression. If you use the word subjected to axial compression, how it can be internal? They will tell, what I told. You just now told. I saw you announcing in the class. Same people who tell wrong concept of what? Internal, they will tell, consider a member subjected to axial compression or consider a cross section subjected to bending moment. They will tell, subjected to bending moment. Subjected to bending moment you are using and you are telling it is internal. How dare you tell it? Of course, what they are telling is, if you apply a axial force this way externally, internal resisting force will come, stresses will come, that is internal. If you apply a bending moment this way, internal resisting moment will come to balance or resist that bending moment. That is internal. But they are telling wrong things. Okay, these all later. I already told so many things here. So this is internal resisting force for resisting externally applied tensile force, internal resisting force for resisting externally applied compressive force. Now, come down. Class. Suppose in engineering mechanics, you are interested not what happens inside the member. See, strength of materials, you are interested in knowing what happens inside the member. But you should write it in both the places. In engineering mechanics, we are not bothered about what happens inside. We are bothered only about the contact point. So, when you consider the contact point here, see, all I am telling you should write. When you consider this side, see, contact point here, or contact point here, or here, this contact point. If a force P is applied here, a balancing force P will come here. Or if we apply a force P here, a balancing force P will come here. This is compressive, this also is compression. See, internally a force will come this way only when a member is in compression. When a member is in compression, then the member will give force like this. Here, see, if you apply a force P here, externally, internal resisting force will come this way. If you apply force P here, internal resisting force P this way. Now, this is tension. More explanation is coming up. Now, I will tell more explanation to make everything clear. 1 minute. This all what I told, go through thoroughly, understand everything. Once again read it. Then I will go to final part, or easiest way to decide or mark, or to show or mark compression and tension, which is required not only for engineering mechanics, for entire structural engineering. Remember. Okay. Okay. Now onwards, see, which is internal? You consider a contact point. See here, this is the contact point. Remember that much. For engineering mechanics, you require. This is the contact point. This is contact point. Someone will ask, what is contact point? I will tell, engineering mechanics, you get it. That's all. It will come later, contact point. Now, see. Now onwards, at a contact point or at a contact point, one of them will be internal, one of them will be external. Remember, see, at a contact point, if I take this way, one of them will be external, one of them is internal. Which is external and which is internal does not matter. You write, does not matter. Compression means which is among these two, which is internal, which is external, does not matter. Here, again, among these two, which is internal, which is external, does not matter. Compression means to the contact point. See, I should be careful, otherwise it will be painful. See, to the contact point, both should act towards the contact point. See, tension means both should act away from contact point, or you can write a crude method. You write, I am not telling, crude method. Crude method. You write, I will write common here. I will put common. See, irrespective of which is internal or which is external, irrespective of that one, if you want to show axial force, compression or tension, use the, already I told clearly, what you do is, to the contact point, both should be incoming, not telephone call incoming. To the contact point, both should be outgoing. Both should be outgoing. See here, outgoing. That is, once again I will tell you. But my hand is paining now, see. To the contact point, if you want to show compression, both are towards or incoming. If you want to tension, this way. This is permanent for engineering mechanics, strength of materials, or any subject in future. Structural analysis also it comes sometime in a roof truss hall. You have to mark tension compression, or once you get that force by seeing the direction, you have to decide tension compression. Okay, I'll give little more examples now. Now, this is all for easy understanding. See, sometimes people will tell level, technical level. I can talk technical level, any level. But my purpose is not to show you my technical level. My purpose is to make you understand. So I should give simple language. Sorry. Someone will ask you in future, show compressive and tensile. Then, see, someone will ask you, show compression and tension externally. Okay, I don't think these are all for compression. Someone will ask you, show compression and tension externally. Answer. Then, see, how to write it? This is a member now. 1 minute. I'll click on this one. Then, what you have to answer you have to give? You show the member here or here. Show the member. Tell them what you want. So you want to show compression and tension both? Okay. This is for compression. You tell them compression sketch is here. See? Or at the contact end point, incoming arrow. Then what do you want? I want to show tension. Okay, tension is here. See? This is tension. Clear? Clear. Okay, then. Or someone will ask you, show compression and tension internally. Okay, you tell them. Then, see, I'm telling compression here. This everything is compression. This everything is tension. Then internally you want, see, you tell them. But they will tell, see, it is right side, left side. Do not talk left side, right side. No. Internally or externally. Or see here, show tension internally. Tell them, external. This way. Or someone will ask you, show compression and tension both externally, internally. Tell him, okay, no problem, boss. Whatever you ask, I got the answer. Both. Tell him. Both you want? Oh, sorry. Compression. Okay. Both you want? Okay. He will keep quiet. This is how to show tension compression, whether externally or internally or both. How you consider will come later. Okay. Now, I'll rub and write here. Some example I'll give and close this one. I decided right now only. No breaks. I'll write in front of you. Okay. Furthermore, I will much more I will explain in strength of materials. See. Now, suppose you take an example. One example. One. Suppose there is a truck. Some truck. In the road, there is a vehicle here. This is the vehicle to be towed. This is what happened? Engine failed. It is not working. It is not, engine failed. Imagine you want to move this way. Your purpose is to go this way in the road. Okay. How to do it? You put a connecting member, some rope. This will start going, okay, this will start moving. As it moves, tell me, this connecting member will be in what? You can think a little. As it moves, surely connecting member, I'll put red color for connecting member. Maybe it is a rope. It can be a rope or cable. It will be in tension. Right here, tension. How? Okay, see, I'll put tension T. Now see correctly, when you consider this vehicle, which is to be towed, or you have to move that vehicle, this tension T is pulling it. See? Yes, but if you consider the truck which is moving, this tension T is pulling it backwards. Therefore, this T will move this vehicle. This T will reduce the speed of this vehicle. See, for this vehicle, this is advantage. For this vehicle, this is disadvantage. If this cable is cut, this will run faster. Or, one more example. Suppose I'll do one thing. Same way, one member here. This is our main vehicle. Okay, main vehicle. So I forgot to put the wheels here. Main vehicle here. One more vehicle is here. You want to move this way. This way you have to move. Now you come from behind. Now if you cannot use a cable. If you use a cable, what will happen? Cable will fold. You require a solid rod. Here, see, here cable will do. Here you require a solid member, solid rod. Then when this vehicle moves this way, it will push that vehicle this way. Now surely this member will be in compression. See how compression? Compression. See now. So when it goes this way, this compression coming from here will push the vehicle that side. So, but this compression is preventing this one higher speed. You can easily make out compression tension here. Now I will come to more. Now this is only for understanding purpose. See, if I am moving this way, if I am pulling something along with me by a rope, that rope will be in tension. Whereas if something is here, if I am pushing it by using a rod, when I push this way, the rod will be in compression. So this is tension, is compression. Now, see. Now, last example 2. When you go to Lami's theorem next class, when I continue Lami's theorem in the next class, not today. Today's class I decided exclusively for this compression tension. Okay. Next class, a question will be given for you. A weight of something, I don't know, a weight of 60 kilonewton is supported by 2 cables. Either cable, see this is either cable, these are both are same, either cable or wire or string or rope, anything, rope. It is fixed here. Now, question will be, find tension in the cable. Tension in cables. Okay. Then, see, I will take the point as O, this is A, this is B. Tomorrow when I solve the question, I may change the name. What I will do is, I will put one more sketch here. See, this is cable. Anybody can tell. When you suspend something, cable will be in tension. Common sense answer. And one more thing, when a cable is given, it cannot be in compression. See, any flexible member cannot be in compression. It can be only in tension. But any solid member can be either tension or compression. Okay, now when I solve the question, I will tell T1 or T1 and T2 be tension in OA and OB. OA and OB respectively. Tension means tension forces, okay. Tension forces respectively. Then I will write one more sketch. See here. How much it is? 60 Newton. See, this is O, this is A, this is B. Okay. How I will write? See, tension. I told so many times. Tension. It should act away from the joint. The force should be outward. And here, this is your T1, this is your T2, and here a reaction will come, RA. RA will come equal to T1. Here, see, this is also tension only. Here, a reaction, RB will come equal to T2. But remember, we want only joint. For Lami's theorem, we want to consider equilibrium of joint O. Joint O. Then, see, then what I will do is, I will sketch a joint O here. Joint, consider, I will write consider joint O. I will put the 60 Newton force or kilonewton or Newton, 60 kilonewton. This is in tension, this is in tension. Tension means should go away. I will put this is T1 and T2. Then I will do one thing, find this angle, find this angle, find this angle, and solve the question. Okay, sufficient. Or I will solve one more question. One more question. Two solid rods of steel or gold also will do. Placed this way, a load is applied from here. Some load, 25 kilonewton. This is O, A, B. It is in equilibrium. Find the forces in the rods. Now, anybody can tell when you have this way, apply load this way, rod will be in compression. Common sense. So, I will do one thing now. Let, what? I write let C1 be compression for OA and C2 be compression for OB. Then I will show a sketch here. A here, B here. There is a force of 25 kilonewton here. Don't tell 25 tomorrow, I won't remember. This is O. I told C1 for OA, compression. See here. Compression this way. Then here also, reaction. There is a reaction here of RA. This is compression C1. This is your compression C2. A reaction will be there. RB equal to C2, RA equal to C1. But our purpose is to find forces in the two members. So our purpose is only joint required. So this much I will explain, but then I will tell, consider equilibrium of joint O. Then see here, 25 kilonewton down. Now, one force in this rod, a force in this rod, a force in this rod. If you apply load this way, already we decided rods will be in compression. It should act towards the point. Tension should act away. I will put C1, C2, find the included angles, and I will apply Lami's theorem. Now, I will close now, sufficient. See, engineering mechanics point of view, sufficient. Lastly, summary. Want to show compression at any contact point. want to show tension at any contact point. That's all. Okay, go through, correctly understand. Very useful for those people. I will tell you one thing. Sometimes, in a roof truss, you require axial forces. Answer will come here. 20 kilonewton, 22 kilonewton, here, 30 kilonewton. I will ask them. It can't be 30, should be lesser actually. Okay, 16 kilonewton. ABC. I will ask them, what is the axial force in AC? Sir, 20 kilonewton. Nature, tension. No, wrong concept. See, they are seeing both together. It is not tension. See, correctly, it looks like tension. If you see both the arrow mark, never and never and never look both end arrow mark. You see one side arrow mark. See here. Compression. See here. Compression. So, force in this member is 20 kN compression. Same thing here also. Force is 22 kN compression. Come to this member. I will ask, sir, compression. No, don't see both arrow mark. See the contact point. See? Or here. Both forces are pulling or going away from the point. The force in the member equal to 16 kN tension. I think some people will now understand. Those who have done B engineering, now they will tell, oh yes sir, correct. Sir, somebody told me a crude method. What is that one? Sometime I also will tell. For very people who find difficulty. Suppose you want to decide compression tension, what to do is very, very crude. Okay. See both the arrow mark. Okay, sir. See, this is very crude. If you see both the arrow mark, tell me, it looks like, sir, tension. No, it is opposite. This is a very crude method. If both the arrow mark together, if it looks like tension, no, it is compression. Ah, got it, sir. Anything looking like tension is compression. Yes, sir. So this looks like tension, sir, compression. This looks like compression, tension. No, you don't tell that way. This looks like compression only or crude method. Urgent emergency. See, if you see both arrow mark, oh, looks like tension. Compression, sir. Looks like tension. Sir, compression. Looks like compression. See, Anthony. He will tell mentally, looks like compression. Sir, tension, sir. Okay, do. But what you do? Not that way. See here. Compression. Tension. Compression. Tension. Any arrow mark from a point going outwards will give tension. Any arrow mark which is acting towards the point will give compression. Okay, sufficient. Tomorrow, next class, I will show you Lami's theorem, closing class. Thank you.